Hello. start at 6:10 p.m. 3 more minutes. Okay, shall I start? It's only you two. I'll just start and other people might join later. Are you there, Venkata? Okay. Can't you hear me? If you can't hear me, then tell me, okay? I'll speak louder. Okay, what is the answer for the first question? Yeah. So here you can see comparator circuit. The flash ADC circuit is given, and you need 2 power n minus 1 comparators for a n bit flash ADC. So here they're asking for a 3-bit flash type ADC. So the number of comparators is 2 power 3 minus 1. N is 3, so 2 power 3 minus 1, 8 minus 1, 7. Option A. Okay. Question number 2. Both of you try to solve it. The question is clear, right? You can see it. Okay. Amit, did you do it? Or do you want me to do it? Do you want some more time to try, or should I just go ahead? Amit Kumar, are you there? Do you want me to give you time to solve it or should I solve it myself? Okay. See, one thing to know about a operational amplifier. This thing is called an operational amplifier, and when it's used in this way, it's actually used as a comparator circuit. So here, when you connect the output, you can see that this output is connected back to one of the inputs. When it is connected to the input that is labeled with the minus sign, that is when it is connected to the negative input, then that is called a negative feedback. One thing to notice about this. Hello, Amit, Amit, is there anything you want to ask? Okay. So when the output is uh, connected back to the negative input terminal, then it's called negative feedback. And when you connect a negative feedback circuit, what this operational amplifier will do is it will try to bring down this voltage to the same as the voltage at the positive terminal. Suppose this you call it as V minus and this is V plus. Then when you give negative feedback, what this op amp will do is try to bring both of those to the same level. But I have already fixed my V plus to 0 volts. So what it will do is it will bring this V minus also to 0 volts. So now you know the voltage at this point. This is 0 volts. And they have given ABCD equals 1010. That is, you have 1 volt here, 0 volts, logic 1 here, logic 0 here, logic 1 here, and logic 0 here. And further, they have given that logic 1 is 2.5 volts. So they're actually connecting 2.5 volts here and 2.5 volts here. These two are connected to 0 volts on both ends. You can see that this is at 0 and this is at 0. So there's no contribution from this resistor. There's no current flowing in that branch, in this branch. So you can ignore this resistor. Similarly, this is at 0 volts and this side is at 0 volts. So you can ignore this 8k resistor also. Now the circuit, if you remove all the extra elements that are not useful for us, the circuit will reduce to this is connected to 2.5 volts. This is at 0 volts. This from here. Wait, I'll mark it. So this concept where both the plus terminal and minus terminal are brought to the same level is called virtual ground. Since plus is connected to a ground 0 volts, then you have a 0 volts at the negative terminal also. So and then you have this RF, that's 1 kilo ohm, and you have V out here. So you can apply a KCL. The current that is coming into this node is the same as the current that is leaving this node. What is the current coming to that node? The current coming to that 0 volt node is current coming here I1. This is I2. This will be I1 plus I2. And the same current will be flowing here. I1 plus I2. So I1 will be 2.5 volts by 1 kilo ohm, which will be 2.5 milliamperes. I2 will be 2.5 volts by 4 kilo ohms, which will be point, how much is it? 6 milliamperes. So I1 plus I2 is 3.125 milliamperes. That much current is flowing in this branch. And if you apply KVL to that branch, you start at 0 volts. Then the voltage drop across the resistor is I1 plus I2 into 1 kilo ohms minus V out is equal to 0. So V out is minus 3.125 milliamperes into 1 kilo ohm, which is equal to minus 3.125 volts. Did you understand, Amit? Or is there a doubt? Okay, then I'll move on to the next question. Which of the following ADCs takes the maximum time for conversion? This, I think it was there. So you can see there are 4 options, out of which last option they are calling it an R2R ladder ADC. So we haven't really seen any R2R ladder ADC. We have seen an R2R ladder DAC. So that option is wrong. It can't be that option, at least not for your assignment purposes. We won't ask you things that are not there in the course material. So among the other 3, you have to remember this table. I am not sure if they've explained how these things are true. I don't know if they've explained why dual slope is fast and why flash ADC or dual slope is slow and why flash ADC is very fast, but they're not explained. You'll have to look it up yourself. So the slowest, there are 3 here. Dual slope is slow, flash is very fast, and successive approximation is medium fast. I've asked which takes the maximum time, so that's the slowest one. It's a dual slope. They're asking which takes maximum time, so it's the slowest. Out of these 3, slowest is dual slope. Okay. What is the resolution of an 8-bit R2R ladder DAC? Assume the reference voltage to be 5 volts. Here you can see, you can see that resolution of a DAC is the reference voltage divided by 2 power n, where n is the number of bits. Here it's an 8-bit R2R ladder DAC, and V reference is 5 volts. So what is the resolution? Try it out. You have the formula here. They have given you VRF is 5 volts, They've given n is 8 bits. So resolution is 5 by 2 power 8. 5 by 256. 5 by 256 will be, and this is in volts. So it should actually be in volts per bit, because VREF is 5 volts and N is 8 bits. It should be 5 by 256 volts per bit, but options are given in terms of volts, so you write that. If you do this calculation, you'll get 19.53. So it's option D. Okay. The thing you have to notice here is there's no difference between a common DAC and an R2R ladder DAC when it comes to the resolution. In fact, the resolution just means the smallest difference that you can detect, and it usually is for 0 volts everything is 0, right? For the number 0, if it's 3 bit or if it's 4 bit, 000 is represented by 0 volts. So the smallest number that's not 0 is 1. That will be represented by the lowest voltage, which is Vref by 2 power n. So your resolution is the difference, the smallest voltage that you can detect. So it doesn't matter what type of circuit it is. If they give some other type of DAC also, as long as you know what is the voltage of the LSB, then that is the resolution. Okay. Try this. It's an R2R ladder network. They have given you the voltage reference. Voltage reference is 8 volts. And there's nothing tricky here. It's just straightforward. It's a normal DAC. And inputs are 1 for all the bits. So it's 1 1 1 1. All the switches are connected to this output 1. None of them are connected to ground. For a uh, what happened? Okay, you can use this result directly. A. Okay, in this you have to substitute 1 for all the B's, because the input sequence is 1 1 1 1. So your output is V out equals, and the feedback here RF is R. So this R and these R's will just cancel. Your output will be negative of, all the B's are 1, So it will be, and all the terms have Vref as common, you can take that out. If you take the reference voltage as common, you get half plus 1 over 4 plus 1 over 8 plus 1 over 16. So this is nothing but, what is the reference voltage? 8 volts minus 8 times. How much is it? You take 16 as the LCM. 8 plus 4 plus 2 plus 1 by 16. Minus 15 by 2 is minus 7.5 volts. Any doubts in that question? No? Okay. Next question is similar, except that here instead of, okay, this is also a 4-bit only, right? Yeah. So here also they have asked a 4-bit R2R ladder deck, but instead of asking the output voltage, they're asking you what should be the reference voltage, given that the output voltage is 5 and the inputs are 1001. Okay. So again the formula doesn't change. It's the same formula. So you can write it as V out equals minus RF Vref. You can take out the Vref common. Vref 2. Does it? B3 over 2R plus B2 over 4R plus B1 over 8R plus B0 over 16R. And since I have, since it's a normal R2R ladder, RF will be equal to R, so it's minus, they're given V out is minus 5 volts. Vref, and you have to find Vref. B3 is 1 over 2 plus B2 is 0, B1 is 0, B0 is 1. This is nothing but Vref equal to 5 into 16 by 9, which is 8.888. So your reference voltage is actually 8.89 volts. Okay. Any doubts? All right. Which of the following statements is true? This is an assignment question, so I can't answer it. Uh, well, you could probably just search it on the internet and you'll find the answer. Binary weighted DAC requires only 2 resistor values. Well, you can see the circuit. From the circuit, at least option D, you should be able to tell directly without knowing anything else. And then The other three options you will have to watch the lecture videos or see the lecture material. Okay, question 8. This is a flash type ADC circuit where the input is 10.13 volts and reference voltage is 16 volts. And they're asking us this circuit what will they have given us the input voltage 10.13 volts. When it is converted to a digital signal by this analog to digital converter, what is the number it is converted to? So what is the digital signal that you get? I'll give you 2 minutes. Why don't you try? See if you can get the answer. 110. Okay. Let Amit and Kannan also try. I'll give them 1 more minute. Okay. What about you, Kannan? Do you know how to solve? Do you want me to give you time to solve it? Okay. What should I call you? Uh, okay. Uh, I'll explain what the circuit does briefly. What this triangle type of thing is, it's called a comparator. It what it will do is it will amplify the difference signal. So if you have a triangle type circuit and you give, let's call this V minus, you'll call this V plus, you'll get some output V out. What this will do is it will give you an output V out, that is some number AV times the difference between your inputs. And if it's an ideal circuit, this AV will be infinite. So that means if you give anything other than 0, that means what I mean is if the difference is anything other than 0, you'll get, if it's a positive number, let's say, uh, actually in practice you can't really get an infinite gain. So let's say it's a very high number, and if your difference V plus minus V minus is positive, then your output will be very high if V plus is greater than V minus, and your output will be very low if V plus is less than V minus. But the thing is, your circuit is connected to some sort of supply voltage, right? Your output will be restricted to only that much amount of supply voltage. So the circuit will actually be connected to some supply. Say, let's say it's connected to 12 volts supply, and here it's connected to minus 12 volts. If it's something like that, you'll have to do a circuits analog AC design course to learn this thing. I'm not exactly sure how the power supply is, but Uh, Very high would mean that it would have to go to some, it won't go to some hundreds of kilovolts and all. It'll just go to the maximum value it can go to and then stop. So it's supposed to give you a very high output, but it'll get saturated. So this V plus minus V minus, output will be something like this. So it will go to some value, the positive supply voltage, and then saturate. So that's the value you'll get. So for our purposes, what we want is that if this difference is positive, then you will get a high voltage, and the high voltage will be interpreted by this 3-bit priority encoder as a logic 1. And similarly, if V minus is larger than V plus, then you will get a low voltage, and that will be interpreted as logic 0 by the priority encoder. That's the working of this triangle type of thing. It's a comparator. It's comparing the values of the voltage at the plus terminal and minus terminal. If the value at the plus terminal is higher than the value of the minus terminal, then you will get a high voltage. If at plus terminal you have a smaller value than the minus terminal, you get a low voltage. The next thing you have to note here is this resistor circuit is just 8 resistors connected in series. So it's a voltage divider circuit. V by 8 volts will drop across each of the resistors. So here Vref is 16 volts, and there are 8 resistors in series. The R equivalent is 8R. So the current will be Vref by R equivalent, which will be 2 by R volts, 2 by R amperes. So the voltage drop across the resistor VR is I into the resistance value. So it's 2 by R into R. So it's 2 volts. That means 2 volts drop across each of these resistors. So this is at 16 volts. 2 volts will drop across the first resistor. So this point will be at 14 volts. This point will be at 12. So it will be 10, 8, 6, 4, 2. And you can notice that these things are connected to the negative terminal of each of the op amps. Now, the input voltage is 10.13 volts. This voltage is connected to the positive terminal of each of the comparator. So you can see for the comparator U7, this one, positive terminal is connected to 14, negative is connected to 10.13. The difference is some positive number, right? 14 is greater than 10.13. Oh, yeah. Yeah, positive is connected to 10.13. Negative is connected to 14. So the difference is less than 0. It's negative. So you'll get a low output here. You can take this as 0, logic 0. Then for the next comparator U6, it's 12 is connected to the negative terminal, 10.13 to the positive terminal. So 12 is greater than 10.13, so this will also be 0. But now when you come here, 10 is actually smaller than 10.13, and all these other voltages, 8, 6, 4, 2, they're all smaller than 10.13. So all these comparators will give you a logic high output. So all these will be 1, 1, 1, 1, 1, and this is obviously connected to 0. Okay. Now, what does the priority encoder do in such a scenario? If it'll see which among the lines which are high, among the input lines which are high, which has the highest priority. So I'm assuming that D7 has highest priority and D0 has lowest priority for this encoder. But the D7 and D6 are off. So since D5 is the highest priority among all these, the output will be 5 in binary. So in binary 5 is 101. So you'll get 101. Start 110 Venkata, it's 101. Okay. This thing only goes from 000 to 111. So 0 to 7 only. It doesn't go from 1 to 8. If there was a circuit which went from 1 to 8, then it would have been 6. The output would have been 6. Since it only goes from 0 to 7, the output is 5101. Okay. Next question is also based on the same concept. You guys try it out and type the answer in the chat box. I'll see if you understood what I told. Only difference here is Vn is 6.25 volts instead of 10.13, but the reference voltage is same, 16 volts. Okay. Venkata says it's C. What about you guys? It's the same method that I explained earlier. This is at 16 volts, so this will be 14, 12, 10, 8, 6, 4, 2. And this thing 6.25. It's connected to the so 14 is greater than 6.25. This will be low. Same with 12, same with 10, same with 8. But 6 is actually less than 6.25. So here you have 6.25, here you have 6. So the difference between the positive and negative terminal voltage is 0.25, which is a positive number. So your output will go to positive saturation limit. So it can be taken as a logical high. So this will be high, this will be high, this will be high. And since this is D3, your output will be 3 in binary because it's a priority encoder. So the answer is 3. Okay. This is also based on the previous circuit. Only thing is here you had 3-bit flash ADCs. So you can see that the output is 3 bits. Now they're asking you what is the size of the priority encoder you need for a 4-bit flash ADC. Yeah, you can see from the circuit that there are the number of output lines in the encoder must be equal to the number of bits that you want. So it must be something by 4 encoder. There's only one option like that, so it should be the first option. And why should it be 16? Suppose you had other options, let's say 8 by 4 or 32 by 4. Well, by construction of this flash ADC, you have 2 power of n minus 1 comparators, and one extra input is connected to ground. Here you can see D0 is connected to ground. So you actually have 2 power n input lines for the priority encoder. So 2 power 4, 16 is. That's why you need 16:4 priority encoder. Okay. Which of the following statements is true? This should also be done in the lecture. Uh, they have given a comparison of advantages and disadvantages, I think. R2 or ladder, only two resistor values, does not require high precision resistors. Disadvantage is lower conversion speed than binary weighted. So binary weighted advantages are simple construction. You can see from the circuit, all the resistors are just connected in parallel. Here R2 are, there's much more going on. Some are in series, some are in parallel. And okay, where did the advantages go? Faster conversion in binary weighted. Disadvantages are it requires a large range of resistors. As you can see, here we are R2, R4, R2 to the N R. So you need a different number of resistors. And if you don't have the same resistor in large quantities, then you can use uh, what I mean to say is there will be resistors with different values. There will be 1k ohm resistors, 2k ohm resistors, but those resistors have to be very precise. You can't use one 1k resistor and another 2.2k resistor. That will give you wrong values. So you need high precision, larger number of resistors. So it can be expensive. Okay. From the options, they were asking about the precision of the resistors. So binary weighted resistor DAC requires high precision resistors. Okay. Which of the following element is essential in sample and hold circuit? So this is a circuit for sample and hold. As you can see, it's made up of comparators and a capacitor. You need those two. And practically when you implement it, you will need resistors and transistors also. But ideally you need only the capacitor. So from this circuit diagram you can see it should be capacitor. Which of the following statements is true? They are comparing the Moore machine and Mealy machine, and they're comparing the uh, output. What does the output depend on in both these machines? See, let's check uh, binary state machines or somewhere here, right? I guess it's not here in this lecture. Maybe it was in week 7. Where is the part on finite state machines? Mealy machine. Okay. This is the Moore machine. Moore machine, the transition of states happens only because the inputs and the output doesn't change. Output depends only on the state, right? See, it should be option B. Moore machine output depends only on the current state. Mealy machine output depends both on the inputs and the state. Option A is also wrong because Moore machine output depends only on the current state. Okay. Any confusion in this? You can see the state machine. From the current state, they have directly connected a combinational logic circuit to give you the output. So the output depends on the current state, that's all. The state itself depends on the input and the previous state. So it's option B. Okay, don't get confused in this. Maybe you would like to go back and read the lecture notes once again if you have forgotten. Okay, it's fine. I also sometimes forget, so I have to go back and check the notes. What is the condition to avoid aliasing effect during sampling an analog signal? What is it? They say I'm not sure if it was explained in the notes, but if you study signals and systems, there they will explain why you have to have a certain frequency and a certain sampling rate. Was it done in class? Doesn't seem like it was done in class. Okay, sampling rate TS. Nyquist rule. Well, they have not explained why this Nyquist rule is true, but at least they've given the rule. So the sampling rate must be at least twice the signal frequency. So that's option A. Yeah. They've just given it in the lecture, but if you take a signals and systems course or a digital signal processing course, yeah, it should be done in a digital signal processing course or a communications course. In those courses, they will explain why it should be at least uh, two times. Or you could just look it up on Google. Maybe you will understand why. This is the final question for today. Which of the following elements is not present in dual slope ADC converter? This is the circuit. You see there's a comparator, there's a capacitor, so there's sampling and holding going on. There's a counter, but there's no DAC. There's no DAC in this ADC circuit. So that is the element that's not present. Okay. I'll just quickly go through all the questions. If you have any doubts in any of them or in any of these topics, you can ask me. How many comparators are required for a 3-bit flash type ADC? From the circuit you can see, for an n-bit flash type ADC you need 2 power n minus 1 comparators. Since n is 3, 2 power n minus 1 is 7. So you need 7 comparators. The following circuit, what is the output when the input equals 1010? Assume logic 1 has a voltage of 2.5 volts and logic 0 has a voltage of 0 volts. So for an operation amplifier, there's a concept called virtual ground, where if you are connecting the circuit, the op-amp in a negative feedback configuration, that is, this output Vout is actually fed back through a resistor to the negative terminal. Then what the op-amp tries to do is bring both of the plus and minus voltages to the same level. And since the plus voltage is connected to ground, your minus voltage will also go to 0. The op-amp will forcefully bring it to 0, and once that is 0, they're given ABCD is 1010, so A and C are both at 2.5 volts, B and D are 0 volts, so and this is also at 0 volts. So when both ends of the resistor are connected to 0 volts, there's no current, there's no voltage drop, there's nothing. You can ignore those resistors. And this one is actually 2.5 volts. They've given that. So the current coming into this RF is the current from both of these resistors, 1 kilo ohm resistor and 4 kilo ohm resistor. And the voltage difference across the resistors is 2.5 volts for both of them. So the current across both the resistors is 2.5 divided by the resistance value. So it's 2.5 milliampere and 0.625 milliampere. So the current that is going through the feedback resistor is the sum of those currents by Kirchhoff's current law. You can use KCL to say that. If you call this current IF, since it's going through the feedback resistor, you can say IF is equal to I1 plus I2. Whatever current is coming here should go outside. And applying KCL here, this current is, let's just say, You can apply KCL here and say IF is equal to I1 plus I2. So 3.125 milliamperes is flowing through the feedback resistor. Now you can apply KVL for this part. You get 0 minus the voltage drop across 1 kilo ohm resistor, which is nothing but IF into 1 kilo ohm, minus V out is equal to 0. So V out is equal to minus 3.125 into 1 kilo ohm, which is nothing but minus 3.125 volts. And one quick check here is the output of your negative feedback connection configuration will always be negative. So you can't get 6 plus 6.25 and plus 3.125. It should be either option A or option C. And to figure out which one it is, you have to do the calculations. Suppose there were three options which were positive, then you could easily conclude without actually doing any calculations that the only negative answer must have been the correct answer, or the options must be wrong, in which case you'll get grace marks. Okay, which of the following ADCs takes the maximum time for conversion? Dual slope ADC. It's the slowest. This is in comparison. Actually, slow doesn't mean that it'll take 1 second to do all this. They'll be very fast. In comparison, some of these are so fast they could be in nanoseconds or microseconds. Some of them, the slower ones, could be in milliseconds. So in that way, I say they given speed as relative. Even the slowest ones will feel fast to humans. What is the resolution of an 8-bit R2R ladder DAC? It doesn't matter if it's an 8-bit R2R or a common binary weighted resistor weighted DAC. In both cases, the resolution is the value of the smallest bit or the smallest voltage value that you can recognize, which is the reference voltage divided by 2 power n, where n is the number of bits. So here the V reference was 5 volts and n is 8. So 5 by 2 power 8 is 5 by 256. So it's 19.53 millivolts. Next question, they have given R2R ladder circuit. Inputs are also given and reference voltage is given. You just need to apply the formula. V out is minus R. This should actually be RF and this can be RF. It can be different than the other resistors. Only thing is it won't be an R2R ladder DAC anymore. At least not the standard DAC, but you could have a circuit like that. Here, since RF is equal to R, all the R's will get cancelled out and all the B's are equal to 1. And Vref is common for all four. So you can take out Vref, you substitute values, you'll get minus 7.5. Question number 6 is similar to question number 5, except that in this case V out is given and they want you to find Vref. So you substitute and get the answers. This is an assignment question in this semester, so I can't help you solve this. Question number 8, I explained in detail how it works. You find out the voltage reference, then that voltage is divided by the total equivalent resistance in this series, resistor series. So there are 8 resistors, so the current will be 16 by, let's say if all the resistors were 1 ohm, the current would be 16 by 8, that is 2 amperes, and the voltage drop across each resistor is 2 volts. So you write down the voltage at the negative terminals of all the comparators. At the positive terminal you have V in, and you compare and you see which comparators are giving you a low output and which of them are giving you a high output. And based on that, since it's a priority encoder, you see which uh, which how do I put this? You see which are the comparators which have 1, and among those comparators, whichever comes at the top, that is that has higher priority. That's how it is. Well, the priority could be designed to be anything you want, but for this circuit, this is the priority, and based on the priority, your output will be some number. Okay, this is also the same as question number 8, except that the input voltage is different and the reference voltage is different. Question number 10, they've asked you what is the size of priority encoder for a 4-bit flash ADC. You can see that the number of outputs in a n-bit flash ADC is the number of output lines that you need in the priority encoder. So the number of outputs in the priority encoder must be 4 for a 4-bit flash ADC. So it should be option 1. The number of inputs will be 2 power n to that encoder. You can see here. For a 3-bit flash ADC, number of inputs to the priority encoder is 2 power 3, 8. Okay. Question number 11, which of the following statements is true? A binary weighted resistor requires high precision resistors. Which of the following elements is essential in a sample and hold circuit? So ideally, you just have a comparator circuit with okay, it's not a comparator, it's a buffer circuit. You have a buffer with capacitor. In a practical scenario, you would need resistors and other stuff also, but the main part of the sample and hold is capacitor. Well, the reason is this capacitor, when current is fed into it, it will get charged and it will hold that voltage and slowly discharge it outside depending on the value of these resistors. So it's actually holding the voltage value for some time. Okay. Question number 13, which of the following statements is true? Moore machine output depends only on the current state, and Mealy machine output depends on inputs and the current state. Okay. Question number 14, what is the condition to avoid aliasing effect during sampling an analog signal? And the sampling frequency must be at least twice of the maximum input signal frequency. This you learn in other courses like DSP. Question number 15, which of the following elements is not present in dual slope IDC converter? And from the circuit you can see that there is no DAC converter in an AD converter, in a dual slope AD converter. You have a counter, you have a sample and hold circuit, you have a comparator also. Only DAC is not there. Okay. That's it for today's class. Does anybody have any specific question that you want to ask? Any doubts that you had? If not, you can leave. I'll just leave it like this for a few minutes. Uh, if you get a question, you can ask. Hello? Hello? Yeah, you want me to explain question 8? Okay, okay, I'll explain. See, for first of all, do you know how this triangle shaped circuit works? This part. Do you know how that works? Okay. See, that thing is called a comparator. What it will do is, uh, let's say this is voltage V1 that is connected to positive terminal and voltage V2 is connected to negative terminal. So by positive terminal, I mean this wherever there is a plus sign in the triangle, and negative terminal, it's minus sign. So the output of this circuit, so usually this type of circuit is built by a circuit called an operational amplifier, and the output of that circuit will be some number AV times the difference between the input voltages, and this AV will be very high. Ideally it should be infinity. So what happens is, if V1 is greater than V2, then this difference V1 minus V2 is positive, and a small positive number multiplied by a very high number should give you a very high output, which is positive. Suppose V1 is less than V2, then V1 minus V2 is less than 0. It's a negative number. Then this AV times that negative number will give you a very large negative number. But since it's physically connected to some voltages and all, it can't actually give you more voltage than the supply voltage. So what it will do is, if V1 is greater than V2, Vout will go to some positive saturation value called plus Vsat. Usually this will be 12 volts or something. And if V1 less than V2, your output will go to negative saturation voltage. Minus Vsat will be something like 12 minus 12 volts. And this thing, well, it need not exactly go to plus 12 or minus 12, but you can understand this as a logic 1, high voltage, and you can take this as a logic 0. So that's all the circuit does. It will compare the difference, it will find the difference between the voltages connected to the positive and negative terminal, and if higher voltage is connected to the positive terminal, it will give you output high. Did you understand that? Okay, now what they are saying is Vin is connected to 10.13 volts. If you see the circuit, that Vin is drawn, there's a line that is drawn, and each of the positive terminals of these triangular circuits, comparator circuits, it's connected to Vin, right? Here, this is connected here, it's connected here to the plus terminal. So what that means is this is 10.13 volts, this is 10.13 volts. So all the positive terminals are connected to 10.13 volts. Is that part fine? Okay. Now V reference they have given as 16 volts. So if you observe this circuit here, you see current can't go into these inputs in this triangle. So whatever current that's coming here, it can't go here. Essentially, it's like this thing is open. It's like there's a break here. So this left part of the circuit will be as if you have connected resistors in series. Have you learned series connection of resistors? In physics you should have seen in class 12. Hello? So what happens in a series connection? The resistance get added up. So since there are 8 resistors here, the current will be 16 volts, which is actually V reference. V reference divided by 8R, just 16 by 8R. And this current flows through each of the resistors. So the voltage drop across each resistor is I into R. So that is 16 by 8R into R, which is nothing but 2 volts. So 2 volts will drop across each resistor. Did you understand? Now you're starting at the top, you have 16 volts. So current will flow here and 2 volts will drop there. So this point will be at 14 volts, right? So similarly, 2 volts will drop across the next resistor. So you will have 40, 12, 10, 8, 6, 4 and 2 volts. And if you observe in the circuit, all these voltages are connected to the negative terminal of the comparator. So this is connected to 40, this is 12. So 10 is connected to the third comparator, 8 is connected to the fourth comparator, so on. Is that fine? So now you know the voltages at both the positive and negative terminal of all the comparators, right? So what will each of these comparators do? Here you have 14 volts. Here you have 10.13 volts at this point. So the plus terminal is connected to smaller voltage. So the difference in voltage is negative, right? So your output is output low, which is 0. Correct. The same thing with this next comparator. This is a 10.13 volts that is connected to the positive terminal, and 12 volts is connected to negative terminal. So to negative terminal, higher voltage is connected. So the difference voltage is negative. So the output will be logic low. When you come to the third comparator, the negative terminal is connected only to plus 10 volts, but positive terminal is connected to 10.13 volts. So the difference between positive and negative terminal is 0.13, which is a positive quantity. So your output is output high. Correct. Yeah, whatever difference it is, you will get a high voltage. uh, it can be just 0.00001 also. Even then it will be the same. Ideally, practically it might not be able to detect such a small value, but 0.1 and all it will detect, no problem. There will be, if you look at the actual integrated circuit for this op amp, they'll give you a data sheet which will give you all the specifications. There they will mention different values, what is the sensitivity, what is the lowest difference it can detect, all such stuff will be given. But for our purposes, 0.13 volts and all is very large, it can detect that much. So since we usually this positive terminal, the voltage there is called V plus, and negative terminal voltage is called V minus. So it will take the difference and multiply it by a large number. Usually, ideally, it will be infinity. So since V plus minus V minus is 10.13 minus 10, it's a positive number, and infinity times a positive number will be positive infinity. But you practically it's not infinity, it's some very high number. Second limitation is it's connected to some supply voltage. It can only go up to that supply voltage level. For our purposes, we can take that as logic high. So that third comparator goes to 1. Similarly, for the rest of the comparators that are, you can see that the input to the negative terminal is less than 10 volts in all those cases. It's 8642. And the input to the positive terminal is 10.13. So in all those cases, the positive terminal voltage is higher. So output will be 1. Up to here you understood, right? Okay, now there was a circuit called priority encoder that was taught in previous classes, right? What this priority encoder will do, it will check the input lines, which of them are high. Among these, there are lots of input lines. D1, D2, D3, D4, D5 are all high, but it will give priority to the largest number. So this particular priority encoder will give preference to D5. And the output of that encoder will be the number 5. In binary, 5 is 101. So the output is 101. Yeah. If you want to understand it better, you can try the next question yourself. And the answer also I have given. You can try it and see whether you understood it or not. Okay. Dr. Vijay Kumar, the session is over. Do you have any question that you wanted to ask? If you had some question, then I can clarify. Anyone else have any question? I'll just scroll through once. You see, ask if you have any question. So flash ADCs. This is binary weighted DAC. Question about R2R ladder. And then this is also on a R2R ladder DAC. And then this is a flash type ADC. 2 questions on that. 3 questions. Sample and hold circuit. Question about Moore and Mealy machine. What's the difference? Sampling frequency and circuit of the dual slope ADC. If there are no other questions, I'll end the session. I'll wait for 3 more minutes till 7:30. Afterwards, I'll end. Yeah, I'll end the session now. If there are any questions, you can ask in the next problem solving session. Okay. Bye. Good night.